Hi, everyone. This is the final presentation for Senior Design Group number 25, Mechanical Engineering. Our project is Delfram, the Mechanical Diaphragm Pressure Gauge. These are some of the topics we're going to talk about today. We'll just take you through our quick motivation and our ideas. We'll show you our design. We'll talk about all the things we did, all the lessons we learned. We'll take you through what this product actually means to the community and to the industry, and then we'll summarize what we did during our time and how we did it. So our motivation was based purely on personal experience. Two of our members had experience in industry, be it power plant, chemical, and petrochemical um, facilities. And what we noticed during that time was a real lack of reliability from the pressure gauges used in the field. Um, what we saw were a lot of incorrect readings, a lot of broken gauges that were just going ignored, and what it would really lead to is complacency in the work field. And this would lead to operators not truly knowing the running conditions of their machinery or the process equipment, and it could lead to safety issues, or simply, less dramatically, it leads to a decrease in plant reliability, which costs obviously money. So our goal was to stop these unreliable pressure gauge incidents and create something that was a little more sustainable and a little more robust for the industry. So these are who we're going to work with. These are designed for places that have terrible process fluids, gas or actual fluid. These would be refineries, chemical plants, power plants, and we have to take into consideration other pressure gauge manufacturers and competitors that we will be dealing with this product, and what kind of products they have out there and what reliability they offer. Our needs are reliable, obviously. It needs to be durable, withstand harsh environmental conditions, high temperatures, high pressures, that type of stuff, and it needs to be an exact fit for the most common gauges out there, like this Ashcroft 1259, which is generally the most used process gauge in refineries, especially. The closer it looks to this product, the more likely that a maintenance worker or an engineer or a plant operator would to be pick this one up on the shelf and to use it as a replacement for these more unreliable Ashcrofts that are out there now. Um, this is what we aim to do. We want to improve safety and industrial reliability by creating innovative pressure gauge solutions, simply put. So how we wanted to complete that goal was to use something that was mechanical, because what we determined was that there's thousands of gauges in a refinery, and 80% of them, 90% of them are mechanical. It's impractical to have data lines and electricity run to every single pressure gauge in a refinery or plant. There's just too many data points to measure traditional or with electronics. It needs to be done traditionally with an operator. So what we needed was something that was mechanical and was consolidated into its own unit, just one singular unit with no additional installation needed. Um, what we wanted to use was a diaphragm. We came up with this idea because diaphragm gauges are already used in refineries, but not like this. What you see on the right is a diaphragm gauge. That's generally how they work. Um, but they look a lot different than a regular pressure gauge. They have this additional flange underneath it, and that makes it physically look different to an operator or a plant worker or maintenance personnel that would be replacing these gauges. It might make them not want to choose it off the shelf. But besides just looking different, the flange changes its size. It's not a drop-in replacement for the pressure gauge that's out there, those Ashcrofts that we're trying to get rid of. Bored on two gauges. So what we want to use is this diaphragm, but use it in a different way. So we decided to still use a diaphragm, but mount it internally inside the gauge, parallel with the gauge face. So it'll work on the same principle of a flexing diaphragm, just it'll look a lot different. It'll look like the classical pressure gauges that we see in the field. But we need to do this adhering, obviously, to the factors, straight safety factors that are out there. There's ASME guidelines, there's API guidelines, all that stuff that we just need to follow for pressure filled devices. And we're going to test it with a physical test rig, or we plan to rather, but we'll get to that later. So when we decided we wanted to make this pressure gauge, we needed some bounds that we followed. So we set up some target specifications for achievable goals during this project. Um, we chose bounds from 0 to 100 psi. It was something that was achievable for us. Uh, Operating temperatures -20 degrees to 200 degrees Fahrenheit. So all the materials chosen have to be able to withstand higher temperatures than that. They needed chemical resistance to a lot of the common chemicals you find in refineries and petrochemical plants. So we used that to determine the metallurgy that we needed for our materials we used inside the gauge. And we wanted an accuracy of plus or minus 0.5%, which is within ASME guidelines for pressure gauges. So specifically, that one on the top has a lot of requirements for these pressure gauges, including that accuracy reading and testing procedures that we would use to test the gauge. And we had other API considerations, things like factors of safety that would need to be built into pressure containing devices such as this. So our original goal for this project before all this pandemic stuff happened, we just wanted a working prototype. We wanted to be able to put it on a test rig and physically measure how close it was to the true PSI in the system. We were going to use that using ASME guidelines, and we were building a rig during this time. But once senior design ended because of the pandemic, we stopped progress on that. After we tested, we wanted to tweak the final design, but that obviously isn't going to happen. What actually happened is we built a semi-working prototype. It was something that we had. We had all the components to all the 3D components. We were one part away from completing the entire gauge, and it seemed like it was on track to work, but there was obviously no way to test that. So what we have is a prototype that seems like it should work, but we just never got the chance to try. So hopefully we do in the future. So this is our basic design. I'll keep it simple here. All the orange and black components you see are plastic. They're made out of PETG. And we like to call them the housings. Right here, back here is the pressure box. That's exposed to the process fluid, and it's screwed right in with a standard connection on the bottom. And right here is the diaphragm, and the diaphragm is a thinner piece of metal that flexes when under pressure. So as pressure builds up behind it, the diaphragm flexes out further or less. And this gearbox over here picks up that deflection and translates it into rotational motion on the needle, and right in the gauge's face. So it'll be 0 to 270 degrees range of rotation, and that'll represent 0 to 100 psi. So these are our designs for the gearbox, at least. It shows 2 designs here, but God, there must have been a dozen. These were the 2 most complete. What you see on the right is the most refined version. It's the version we settled with for now. It translates that linear motion to rotational motion very well. Little backlash, little leeway between the gears, so it was as accurate as possible as 3D printed parts can be. We used steel rods and bearings instead of all plastic components for the second piece. There was a lot we changed. We changed a lot with our pressure box too, but we were able to do that on the fly. So there was only one iteration of the pressure box, and the housings and the gearbox took a lot of tries. It was a lot of fine tuning and a lot of step-by-step refining. This is an example of one of our FEA analyses. We did a ton. We use these to verify the calculations that we've done based on published documents and formulas that are out there on the internet. We use those formulas to calculate theoretical deflection of a disc like this. And it gave us a number that we were pretty confident was right. And we used our FEA analysis to determine if it truly was right and validate our numbers, and they were pretty close. So we went ahead with our design, and it also helped us determine deflection and stress on the disc, so that helped us with factor of safety. So I have here a demonstration of what our prototype actually looks like, because physically I can't show you, but I can show you taking it apart. That's a retaining ring. It just twists to unlock the front cover, and a piece of plexiglass that we use to cover our needle and internal components to protect them. There is an O-ring in there that seals it from the outside, and in the back there's an O-ring that I've taken out beforehand, but it goes there. The screw design in the back, the bolt-up design, is very similar to the gauges that are out there right now. The housing itself, the actual physical aesthetics of it, is very similar to current gauges used. That's the outer housing there. This is the pressure box, held with 4 screws, much like a flange, of that size, rather. And the diaphragm sits in between those two components, those two screwed-down components. And there's an O-ring that seals. This is the gearbox, and it rotates like that. A little push of the plunger in the back moves the needle. There's usually screws that hold that front cover in, but they've been taken out for ease of this video. And that's it. Pretty slick. It uses gears and rods. So data for this project. That is our blind spot. We have no data of testing. We were in the process of building a test rig to ASME standards when COVID happened. So we have a half-complete test rig that'll never be used. We were going to use that to get our data on accuracy compared to a gauge testing kit, but we were never able to do that. So yeah, and the last thing we left, we halted the order of our diaphragm. We had a special order, and we stopped the order being when we knew we weren't going to be able to complete the project, and that's kind of where we ended. We were able to conduct in-field interviews and get some data from that, albeit not scientific data. We have what engineers see from our co-op experiences. What engineers see as failure points, how often you see gauges, and if you're actually satisfied with the gauges that are out there. And we got great responses, a lot of responses back. And as you can see, the most common time you see a gauge is weekly. They see a gauge every week that's broken. The other half of the people almost see it daily. I noticed that the daily people were generally maintenance workers, and the weekly people were generally engineers. We see a lot of vibration, clogging, overpressuring, and process pulsation, and we look to target the process pulsation, the overpressuring, and the clogging with our product. What we learned was that the prototyping took a lot more time than we thought it was going to take. It was a constant build and redo process, especially with 3D printing, where it's a science, but it's not really an exact science. There's a lot of fine tuning that needs to be done. And we didn't really account for the time, so we had to put in a lot of extra hours to make up for that and stay on schedule. What we did learn from this project is that it's really hard to find data on failures for pressure gauges, because a lot of pressure gauge companies aren't going to reveal how quickly or how their pressure gauges fail. And a lot of other refineries and chemical plants, they really don't care enough to have somebody's full-time job tracking pressure gauge reliability. So there's not a lot of published data out there that confirms the validity of our project, and that was a real gray area when we were choosing this design. And the other thing we learned is that we need to conduct a test rig sooner so that we can perform an actual accuracy analysis on the gauge we created. So these are some of the things we used to construct our gauge. As far as the pressure box went, the stuff that was heavy duty that had to be exposed to the process, fluid and pressure, was made out of Schedule 40 piping and other 304 stainless steel components that were machined. The front glass was made out of plexiglass instead of real glass because we figured that would be a pretty big problem if there was a leak and real glass went flying everywhere. And as far as the housings and all the plastic components, they were made out of 3D printed material. Specifically, we used PETG because of the high resistance to temperature, and it was higher than those plastics used on gauges already in the field. So to build these parts, we used obviously a 3D printer for the plastic components, and as far as the metal components went, we used pretty basic things: lathes, drill presses, um, saws, stuff like that. The construction was not incredibly complicated, but it was extremely time consuming, and our machinist there and group member Nick did a fantastic job with that. Some software we used to build this product. As far as the 3D components went, we used Autodesk Inventor to draw all of them and a Prusa slicer to convert that into G code for the Prusa printer. And as far as the FEA analysis went, that would be done on Abacus. This is a big one. Context and impact. We had to look at a little economic impact. We wanted to make it affordable for all the people, and a price range that was extremely similar to the gauges that are already out there. So it was important that we keep our costs down. But working gauges, more reliable gauges, can lead to better reliability and lower costs for those facilities. Environmental impact. There's loss of containment of these chemicals. That would be a major problem. So we need to, keep that in consideration, especially when we build our factor of safety. And construction methods, we need to make sure they're environmentally friendly. As far as the social impact goes, it needs to be accessible to refineries. It needs to be accessible to those personnel that use it, and an ethical analysis. Our main goal is safety here. Our product needs to be safe for the operators and the people working in the plant. So in order to prove this, we used our FEA analysis. We used stress calculations, factor of safety of 6, and we would use physical testing to test that boundary to make sure it was safe for the operators. So this is what we accomplished in this whole project. We did a lot of research on metallurgy and what we would need, standards we would need to make this gauge. We conducted surveys of all the people we've ever known in our co-ops that are in the industry to see what they thought, to see the reliability they saw, and to see the problems they faced. We created multiple prototypes and variations. As far as poster day went, we brought 2 of those completed prototypes, full prototypes like you see in my hand. Brought 2 of them. That second one obviously worked better than the first. We conducted FEA analysis to make sure that our design was safe, and we produced a viable theoretical working prototype. Something that if we put it on a test rig, the needle would actually move, and we would be able to test accuracy. And we're very impressed with that mountain that we were able to overcome. It was a big challenge, and each one of our group members rose to the task. And we put in a lot of hours and a lot of work to make this thing happen, and we're very proud of it. And I think it would have been really nice to test this to see how accurate it really was compared to gauges in the field. So things we faced as a team. We worked really well together. We've worked well on projects before, and communication and openness was the main strength of our group. We always work well together and very professionally. And keeping a good schedule, thanks to Julia, our project manager. We stayed on track. We needed to get testing and testing methods done earlier. We kind of left that to the end, and we needed to really be on the ball with that. Finding a diaphragm, it's a difficult part, and we should have started looking earlier. And we needed to get the right data in the beginning, which was difficult to prove the viability of our product. Prototyping obviously took a lot more time than anticipated, and it was an iterative process, as I've said before. And the testing, especially testing rig in the future, needs to be developed simultaneously with our actual product so that the testing org will be ready when our product is ready, and that would have avoided us not actually being able to test it at this time. As far as lessons that we can teach the incoming senior design students, uh, use online storage. We use Microsoft Teams. It went absolutely fantastically. People were able to access Excel, PowerPoint, and Word documents, reports right on their computers, phones, whatever, wherever. It was incredibly easy to work with, and it helped keep us all on the same page. Um, we tried our best not to rely on Drexel facilities. We wanted to do this with our own machines that we had, own lathes, stuff like that. And if you are able and you are afforded the opportunity, try and do it on your own. Try and do it outside of Drexel, especially if you're looking to pursue a product after senior design. Um, and we would like if it was set up a little bit differently where we were able to pursue our idea and funding for our idea earlier than what we did. We held off on a lot of things, ordering more expensive materials until we procured our box diver. So if we were able to get that process going quicker, it would really help us along the timeline to get our product done quicker. This is our budget. As you can see, it's still pretty low. We only spent about $260 on all our things. Biggest cost was materials for machining, to make sure we had right tolerances and stuff. Uh, this is our timeline. Um, we would be able to theoretically follow the schedule through the rest of the year. We were on track, but we were unable to meet our goal. As you can see, testing and manufacturing new parts for another prototype was put on hold. But we're very proud of what we did. And I thank you guys for staying and listening to this presentation all the way to the end. I wish you all the best. Stay safe, and thank you. Thank you for giving us the opportunity to pursue this project. We had a lot of fun, and we learned a lot. We learned a lot from our professor, Young Cho. Thank you, Professor Atchison, and thank you, Nick, Julia, and Anthony, for all your help on this project. We all worked as a great team, and I appreciate all the professors that helped us along the way. Thank you, guys. Have a great day. Stay safe.